Welcome to this explainer. Today, we're going to break down the foundational math behind machine learning. We're starting with those simple equations you probably remember from algebra class, and we're going to build all the way up to how those exact same concepts literally power modern AI. We're bridging the gap between the blackboard and the black box, showing you exactly how these, dusty textbook concepts are actually the vital beating heart of modern tech. So if you've ever wondered what's mathematically happening under the hood of a massive neural network or an image compression algorithm, you're absolutely in the right place. Let's get into it. Here's our roadmap for today. We'll start with solving linear equations, move on to the row reduction method, tackle singular versus non-singular matrices, and finally, look at machine learning applications. Section 1. Solving linear equations, the foundation of matrix algebra. Okay, so any standard system of linear equations, no matter how massively complex it gets, can be elegantly rewritten in this super simple matrix form, AX equals B. Think of A as a grid holding all your known coefficients. X is just a vertical list of the unknown variables you're trying to find, and B represents the target results. By organizing our data this way, we shift from wrestling with messy human-readable algebra to performing really clean, structured matrix operations. And this abstraction is incredibly powerful. For a computer, solving 10 equations or 10 million equations suddenly uses the exact same fundamental architecture. Instead of tracking individual variables, the machine just manipulates blocks of numbers all at once, which is, of course, exactly what modern computer processors are built to do. So, we actually have a few options in our toolbox for solving these systems. For really small problems, sure, you might use substitution or elimination by hand, but as things get larger, we need systematic, algorithmic methods. There's Cramer's rule, which uses determinants to find solutions, but honestly, it gets computationally heavy super fast. Then we have row reduction, which we're going to cover in depth in just a second, and we also have the matrix inverse method, where we basically divide by A, or more accurately, multiply by A inverse. But there is a massive catch here. The inverse method only works if our matrix is perfectly square, meaning the exact same number of equations as unknowns and something called non-singular. If those conditions aren't met, the inverse method just completely falls apart, which is exactly why we need more robust tools. When we're solving these equations, we generally encounter three possible outcomes, and they all depend on how much true information our matrix actually holds, something mathematicians call rank. If everything aligns perfectly, boom, we get a unique solution, one specific definitive answer. But sometimes equations just contradict each other, like saying x plus y equals 2 and x plus y equals 5. Think of these like two parallel train tracks, right? They are never going to intersect, which gives us absolutely no solution. Alternatively, the equations might just be repeats of each other, overlapping perfectly. This leaves us with infinite solutions because we essentially just have a whole line of possibilities and not enough unique, constraining information to pinpoint a single dot on that line. Moving right along to Section 2, the row reduction method, simplifying matrices systematically. So the Gaussian elimination algorithm is this completely safe, highly systematic way to simplify a matrix. We use three safe row operations. We can swap two rows, we can scale a row by multiplying it, or we can add a multiple of one row to another. Doing this doesn't change the underlying truth of the equations at all. It just strategically alters how they look. We basically isolate a pivot number, zero out everything below it, and repeat. Fun historical fact for you. Carl Friedrich Gauss formalized this exact method way back in the early 1800s just to track the orbit of the asteroid Ceres with incredibly limited data points. Today, this step-by-step logic is exactly what massive math libraries like NumPy are effectively doing under the hood to solve complex systems in a fraction of a millisecond. It's pretty wild to think about. What we're trying to do here is transform our messy starting matrix into one of two highly organized states. Row echelon form, or RREF, is kind of like a neat staircase of ones stepping down to the right, with zeros below them. But reduced row echelon form, or RREF, is the true holy grail of this whole process. Here, we've cleared out the zeros both below and above our pivots. Why is that so absolutely crucial? Well, by eliminating every other number in that column, we've completely isolated each variable. The math stops being a puzzle. In this state, the matrix is so thoroughly simplified that the aha moment hits. You can literally just read the final values of your unknown x variables straight across the rows. The matrix has effectively solved itself. All right, Section 3, singular versus non-singular, the information analogy. This entire concept really just boils down to an information analogy. A non-singular matrix is the good kind. It has a non-zero determinant, it's fully invertible, and most importantly, it's packed full of independent, unique information. Every single row tells you something completely new about the system. A singular matrix, on the other hand, is broken. Its determinant is mathematically zero. Why? Because geometrically, the matrix is literally collapsing in space. It's losing a dimension because some of its rows or columns are just disguised combinations of others. The information isn't unique, it's redundant. And when a matrix contains redundant information, it has less than full rank, meaning we're missing the critical pieces we need to find a definitive answer. Let's put this intuitively. Imagine you're trying to solve for two unknown variables, and I promise to give you two clues. Clue number 1 is x plus y equals 5. Clue number 2 is 2x plus 2y equals 10. At first glance, you might think you have two helpful equations, but take a closer look. You really don't. That second equation is literally just the first one multiplied by 2. It is completely dependent, it's entirely redundant, and it adds absolutely zero new information to your underlying problem. You've been tricked into thinking you have more data than you actually do. And that specific redundancy is exactly what makes the matrix representing those equations completely singular. So think of rank as a highly sensitive, unique information detector. It doesn't just blindly count how many rows or columns you have, it counts how many of those rows are genuinely mathematically independent. Imagine you're managing a team of 5 workers. If 3 of them are actively solving problems, but the other 2 are just blindly copying whatever the first 3 do, your actual functional rank of productivity is really only 3. You don't really have 5 independent workers. It's the exact same thing with matrices. A non-singular matrix has full rank, meaning zero redundancy, while a singular one operates with hidden deadweight. Which brings us to Section 4, Machine Learning Applications, the AI Payoff. Okay, so the math we just covered isn't just academic theory. It is the literal beating engine of artificial intelligence. This is the exact moment where high school math transforms into cutting-edge modern tech. It drives absolutely everything in the field. We're going to look at how we can use the concept of rank for advanced image compression. We'll see how massive neural networks are fundamentally built directly on top of these linear equations. And we'll explore how we strip away massive amounts of computational complexity using principal component analysis, or PCA. This is where the magic actually happens. Think about an image on your computer. It's essentially just a massive matrix of pixel values. Now, picture a high-resolution photo of a clear blue sky. There are thousands upon thousands of pixels that are exactly the same shade of blue. That is highly redundant, dependent data. Because we understand the concept of mathematical rank, we can intentionally drop that redundant singular data. We can mathematically approximate the image with a much lower rank matrix. We might drop the rank of the image matrix from 1,000 down to just 50. We keep only the most crucial, mathematically independent structural info. As a result, your eye won't even notice the difference in the picture, but your computer's hard drive definitely will, because the file size is drastically reduced. It's pretty amazing. Furthermore, think about the architecture of modern deep learning. Every single layer of a multi-billion parameter neural network is, at its absolute core, just a linear transformation. You take an input vector, which is your raw data, and you multiply it by a massive weight matrix. Then you add a small bias vector to tweak the result. Weight matrix times input plus bias. Take a step back and realize what that actually is. It's literally just a massive, highly iterative version of the exact same AX equals B equation that we started this entire journey with. By systematically adjusting the numbers inside those matrices, the network actually learns to transform messy, real-world inputs into highly accurate predictions. So, let me ask you this. If matrices, rank, and linear equations are the actual engine driving artificial intelligence, how well do you know your engine? Understanding singular matrices and the precise logic behind row reduction isn't just pure abstract math for the sake of math. It's the fundamental, underlying architecture of the algorithms actively shaping our future. You simply cannot build a solid, towering house without fundamentally knowing how the bricks work, right? Mastering these core linear algebra concepts is exactly how you understand the bricks of the AI revolution. If you're ready to master this engine and you want direct access to the exact running math notes we use to build this explainer, I've got you covered. Just drop a comment below and I will personally send you the link to the complete notes. It's an incredible resource to have in your back pocket. Thank you so much for learning with me today, and keep exploring the math behind the magic.